Good afternoon, sir. Good afternoon, everyone.
Good afternoon, sir.
Am I audible, sir?
Yes, sir.
Okay, thank you, sir. On behalf of Sri Siddhaganga College of Arts, Science and Commerce for Women, Tumkuru, I warmly welcome you all to Day 2 of 6 days National Level Faculty Development Program on Research Methodology for Experimental and Theoretical Sciences organized by the Departments of Science. I hope all the participants had an enriching learning experience during yesterday's inaugural session and the first day technical session. We are delighted to continue the academic journey today with another insightful session. Dear participants, a small request. As this session is being conducted through Google Meet, it has a limitation of 150 participants. If anyone faces any difficulty joining or experience any technical issues, we kindly request you to join the session through the YouTube live streaming link already provided in the WhatsApp group. And thank you for your cooperation. Today's resource person is Dr. Suresh Kumar HM, Professor, Department of Physics, Siddhaganga Institute of Technology, Tumkuru. He will be delivering a lecture on the topic Nonlinear Optical Crystals from Fundamentals to Photonic Applications. This topic is highly relevant in a modern scientific research as nonlinear optical materials play a vital role in a laser technology, optical communication, and photonic devices. Before we begin the session, I would like to request all the participants to kindly keep your microphones muted and post your questions in the chat box. We will have an interaction session at the end of this particular session. Now, I would like to request Pratibha ma'am from the Department of Physics to deliver welcome and introduction of today's resource person.
Good afternoon, everyone. Myself, Pratibha, from the Department of Physics, lecturer. So it is my privilege to introduce our distinguished guest speaker, Dr. Suresh Kumar HM, Professor and Head of the Department of Physics at the Siddhaganga Institute of Technology, Tumkur. Dr. Suresh Kumar was born on 25th April 1973 in Kottur, Bellary district. He completed his MSc in Physics in 1995 and MPhil in 1996 from the Gulbarga University. He later obtained his PhD in the physics in 2004 from the same university. So he has more than 20 years of teaching experience. Since 2007, he has been serving at Siddhaganga Institute of Technology, Tumkur, and since 2014, he has been heading the Department of Physics. Under his guidance, 5 PhD scholars have been awarded their doctorates, and 2 research scholars are currently pursuing their PhD under Vishwesvaraya Technological University, Belagavi. So Dr. Suresh Kumar sir has successfully completed a funded research project worth 30 lakhs from the Vishwesvaraya Technological University, Karnataka State Council for Science and Technology, so from the government of Karnataka. He has published more than 50 research papers, reputed international journals. In addition, he serves as a doctoral committee member for many research scholars at VTU and other universities, and has contributed academically as a board of studies member for several autonomous institutions, including BMS College Engineering, BNMIT Bangalore, Ambedkar Institute of Technology, and Bellary Institute of Technology. So, thank you one and all.
Thank you, ma'am. Now it is privileged to invite Dr. Suresh Kumar HM sir to deliver his expert talk and share his valuable knowledge with us. Sir, the virtual platform is yours.
Screen sharing.
Just 1 second, sir. I'll start it.
Yeah, yes. Dear participants, there is a small technical error in the speaker side. Please hold on for a minute or 2 minutes.
Good afternoon to one and all. Am I audible now?
Yes, sir, you are audible, sir.
Just a minute. Just you check it. The slides are moving.
Yeah, sir, it's moving, sir. Please go ahead,
Thank
sir.
you. Thank you. Good afternoon to one and all. Thank you for giving the introduction, ma'am. Now I'm going to give a talk on nonlinear optical crystals, preferably fundamentals to photonics, photonic applications. Of course, the topic what I selected is little bit physics related topic, where the faculty members can do some research and can publish in a reputed journals within the facilities which are available in their laboratory. Okay. The talk is like this. So first, I would like to give the introduction to the crystals, then methods, how to grow the crystals in laboratory with particular techniques, and what is the importance of doped organic or semi-organic crystals. Then some results what I obtained by my students that I would like to share, preferably by considering the significant crystals which are having wide applications, that is KDP, that is potassium dihydrogen phosphate, ammonium dihydrogen phosphate, and their photonic applications. So regarding the crystals, as you all know that when you consider the solid, you can classify the solids as crystals, amorphous, and polycrystal materials. So you can distinguish those three based on their distribution of atoms, as well as the periodicity over the space. So if you consider the crystal, in that one, the atoms or molecules or the ions are distributed uniformly and periodically over the space. And hence the crystals are having a definite shape. The scientific study of the crystals and how the crystals are going to form, that can be studied using crystallography, that is called as crystallography. The process of the crystal formation by certain methods is called as crystallization and also called as solidification. I hope you would have observed some of the crystals in the nature also. So the first figure that you can see the crystal growth in the nature, especially in the winter season, whenever the environment is having some moisture. So during that time, you can see the crystal formation in the nature. Even you can grow the crystals in the laboratory for specific applications. When you consider the single crystals, they have long range of atomic order of distribution, which is extending up to a few atomic diameters. And that structure is going to repeat it for the space. Whereas in case of amorphous or the polycrystals, of course, in the amorphous, even though the atoms or molecules are bounded, but they have a short distance of distribution. That is, short order of exist will be there. Whereas in the polycrystals, the crystallines are oriented in random directions. And also the sizes are not uniform. And hence, people are focusing much on single crystals. Of course, the single crystals are more difficult in practice to growth than the polycrystal. However, the single crystals are having wide applications, and hence it is necessary to grow the single crystals preferable for wide applications. Due to the recent developments in the field of semiconductors, transducers, polarizers, infrared detectors, ultrasonic wave generators, solid-state lasers, piezoelectrics, acoustics. So like that, there are, even if you consider crystalline thin films for the microelectronics and computers they are using. So because of these wide applications, the scientists are thinking to have the crystals, single crystals, for specific applications. So modern different diffraction technologies and spectroscopic approaches are using to investigate and analyze and comprehend the results, how the crystals are formed, what about its transparency, what is thermal stability, what is its optical applications like second harmonic generation, third harmonic generations, micro hardness. So all these parameters can be analyzed to know its potentiality for the photonic devices. These are the few applications just for highlighting where you can use the crystals. So we're going to use the crystals as the optical switching, laser modulators, as I said, harmonic generators, preferably symphonic, third harmonic generators, piezoelectric devices, holographic devices, and also we are using this NLO crystals for the optical communications, The main reason is that, so whenever you apply the electric field across the crystals, the refractive index of the crystal going to change. That is nothing but by references. That is the important concept about the crystals, where they can use the crystals for different applications. So these are the few applications where they can use with the certain figures. As I said, we are going to use these crystals for the generating the specific frequency of signals, and even you can use the crystals for transmitting the radiations. So how you can grow the crystals? So based on the phase transfer process, the crystals can be grown either from solid, growth from solid, growth from vapor, and growth from liquid is also called as solution growth. I would like to highlight how the crystals can be grown from liquid, that is solution growth, rather than solid as well as from vapor. So what is this solution growth? So in this case, we are going to dissolve this solute, that is nothing but the material, in a particular solvent like water in a supersaturated state. This approach is used for materials possessing higher solubility, and also that solubility should depend on temperature. So that is going to help in achieving the supersaturation, and hence you can grow the crystals. So what is this supersaturation? As you know that whenever you dissolve the solute in a liquid, it is going to dissolve if it is mixing. So the supersaturation refers, so as the concentration of the solid goes on increasing, of course, the solubility is also increasing. So the supersaturation refers to a state in which the solution contains more dissolved solute than it would normally hold at equilibrium at a particular temperature, means at a given conditions. That is called as supersaturations. The crystal growth takes place mainly in two steps. One is called as nucleation. So that is going to growth into a bulk crystal. So what is this nucleation? So in the supersaturated system, when few atoms or more than two or atoms or molecules get joined, so because of change in the energy during the formation, so cluster is going to form in the beginning. So this cluster is termed as embryo, and that embryo may grow to a particular size known as critical nucleus, that is acting as an active center. Then the probability for the nucleus to grow into a crystal. So like this, the crystal is going to develop under the supersaturated state. So when you consider the types of solution growth, there are two types. One is slow cooling method, that is nothing but temperature reduction method, and other one is slow evaporation method. So these are the two methods under the solution growth. So what is this slow cooling method? In this process, the saturated solution of the desired compound for which you want to grow the crystal, first you need to prepare the saturated solution a little bit higher temperature, and then the temperature of the solution going to reduce in small steps, like even 0.1 degree Celsius per hour. So in such a small steps, we need to decrease the temperature to attain the good crystallization, means to get the good crystals. So by doing so, the solution which is just saturated at that temperature, initial temperature, will become super saturated. Since as the temperature drops, solubility decreases, because as the temperature increases, solubility is also increasing. Now the temperature is decreasing, and hence the solubility is going to decrease, and hence the system is going to achieve the supersaturated solution. So once the supersaturated solution is achieved, the growth of single crystal is going to be possible. The crystallization initiates in this process, generally not at high temperature. So we are going to select it in the range from 40 to 60 or 70 degrees Celsius. That is the range that we are going to select. We want to go for the higher temperature. So the disadvantage is that, as I said, if you use the temperature reduction method to grow the crystal, we need to decrease the temperature in a systematic manner at slower rate, that is 0.1 degree Celsius per hour. Even 0.01 is also too good. So it requires programmable temperature control. And then wide range of temperature may not be desirable as the properties of the crystal changes at temperature, because as I said, we need to consider the higher temperature, not too much. It should be in the range 40, 45 to 70 or 75, like that. We should not go beyond that, because that many of the physical properties, many of the crystal properties depend on the temperature. So that's why we should not go at higher temperature for the crystallization. Next one is the slow evaporation method. So the experimental setup is almost similar to the previous one, that what I said, that is slow cooling technique. So here the crystals will grow from the saturated solution at constant temperature. So here we are not changing the temperature from higher to lower. We are going to maintain the temperature, preferably the room temperature. Okay. So under this temperature, we are allowing the solution to evaporate it slowly. Means in a controlled manner, we are making the solvent to evaporate. Because the vapor pressure of the solvent is slightly higher than the solute. Therefore, the solvent molecules are going to evaporate, and hence the supersaturated solution is going to be created. For example, just for the reference, it is if you take 40 grams of solute in 100 ml is considered as the saturated solution, let us say at room temperature about 35 degrees Celsius. Now the solution is allowed to evaporate at the same temperature. Now we're not going to decrease the temperature, we are going to maintain the temperature, let us say. So after a few days, let us say 3 days or 1 week, let us say, the 100 ml becomes 70 ml because the solvent is going to evaporate. Now the solute is same, only but solvent is reduced from 100 ml to 70 ml. And hence the solution is going to achieve the supersaturated state. So what are the merits of slow evaporation? So of course it is a simple growth apparatus where we don't require any sophisticated instrument like temperature controller, because we are going to maintain the constant temperature but enough. And using this one, you can get the crystals which are free from the dislocation defects and allows the crystals very well below its melting point. That is also one of the important parameter. And the most one is that you can grow the crystal to a larger size, because for potential applications, especially in photonic devices, the size of the crystal is significant. Even though there are merits, it has, but still it has some drawbacks also. So the demerits in the sense that the solute what you selected for growing the crystal, that should not react with the solvent. That is the most one. And second thing is that the substance what you selected should dissolve completely in the selected solvent. And then in this one, the growth rate is very, very slow, and hence the crystals are going to grow not in 1 or 2 days. Sometimes the crystals may grow in 2 weeks, 3 weeks, month, 2 months, 3 months. So like that, you need to wait till you get the specific size of crystals. So in the next one is that in the grown crystals, inclusion of solvents may be present sometimes. So these are a few demerits, but still we are using the slow evaporation method because it has some few advantages. So because of that, the slow evaporation technique is the best method to grow the good quality with bulk size, means larger size envelope crystals. So this is about a little bit about introduction to the crystals. Now, what is NLO? that is nonlinear optics. I won't go in depth of the nonlinear optics. That I'll give surface idea about meaning of nonlinear optics, and then second, harmonic generation. What is the difference between linear and nonlinear optics? So when you consider the linear optics, it is about interaction of weak light with the matter. Under the weak intensity of light, the frequency or energy of the light does not change. And expression for the polarizability upon interaction of radiation, that is P equals to, that is the equation, that is epsilon, permittivity, susceptibility, and the electric field which is induced. So when under the, it is a 2-photon process. The left side figure, that what you can see here, it is the energy level diagram, and this is the molecule. So when the light is passing through the molecule, so energy of the light is not changed. Whatever it is observed, the same light is emitted. So it is a 2-photon process. It is. So what is this? Next one is nonlinear optics. So this is about optics of high intensity of light. Whenever you apply the highly intensified light like laser, then you can expect the non-linearity in the material. So the induced polarization depends non-linearly with the electric field strength. So we have the first term is related to linearity, and higher order terms represent the non-linearity. And the number of terms depends on the strength of the field that applied across the material. So in this case, as I said, the first one is the linear susceptibility, and second one and third one represent the second and third order. Hello. Am I audible?
Yes, sir.
You are audible.
Yeah.
Generalized, universalized.
Okay. So this is about the nonlinear optics. Now you can observe the figure here. This is the same molecule. In this case, in case of nonlinear optics, when the high intensity of light is passing through the molecule, now you have the new color. Means the energy of the light is changed. So how it is changed is slightly explained here with this energy level diagram. It is a 3-photon process. It means the 2 photons of same energy is absorbed simultaneously, but it is emitting 1 photon. 2 photons of absorption and emitting 1 photon, and energy of that emitted photon is twice the energy of observed photon. Means it is frequency is doubled, wavelength is reduced to half of that.
ಇನ್ನ ಎಷ್ಟು ಹೌದು ಗಾಳಿ ಬರ್ತಿತ್ತಲ್ಲ ಸ್ವಲ್ಪ ಗಾಳಿ ಬರ್ತ ಚಲೋ
Hello, madam.
ಹೌದು ಎಲ್ಲ ಗಿಡಗಳು ಇರ್ಲಾರ್ದಾವ ನಮ್ಮ ಆಫೀಸ್ ರೂಮ್ ಆಗ್ಯದ್ರಿ
Okay. This is about how the non-linearity occurs with the graph.
ಅಷ್ಟೇ ನಮ್ಮ ಇದನ್ನ ಇಷ್ಟು ಸಿಟ್ಟಿಗೆ ಬಂದಾನ ಪ್ಲೀಸ್
Ashwini madam,
Nodi, they are organizers.
Ashwini madam, please mute your this one now.
ಸರ್ ಹ್ಯಾಪಿ ಅಲ್ಲ
Please mute the mic.
ಆಗಿತ್ತು ಅದಕ್ಕೆ ಬರೀ ಚಾ ಕುಡ್ದೈತಿ
Ashwini madam,
Tell them to mute.
ಒಳಗ್ ಬೇಡ ಧೂಳದ ಧೂಳ ಇರ್ತದೆ ಟೇಬಲ್ ಕೂಡ್ಲಕ್ಕೆ ಅಲ್ಲೇ ಕೂರ್ತಿದ್ದೇನೆ ಒಳಗೆ ಸ್ವಲ್ಪ ಜನ
sir, host can also mute this one. Please, whoever is the host.
Madam, please unmute your mic.
Oh, they can't listen now because they are in the other side, so they won't mute. So kindly advocate, please mute us.
We don't have accesses. Only the host can mute them. Otherwise themselves can.
Who is the how to? Oh, okay, I think. Okay. So here, why the nonlinearities occurred in the material? Because whenever you increase the intensity of light, the dipole moment is also increased. Because of that, the nonlinearity going to achieve here. So this is about the nature of graph, so output or the polarizability as a function of input intensity of the input light, which is changing non-linearly. So you can see the graph together about linear response and non-linear response upon applying the electric field. So this interaction behavior of light within the materials that helps to understand how the refractive index and absorption ability of the material changing and extend their applications in the fabrication of the various optical elements like polarizers preferably, and then electro-optic devices, filters. So that is going to achieve using this nonlinear response field. Okay. So when I said that how much of intensity of light we supposed to select to increase or to make the material to non-linear. So the strength of the field, electric field of the light wave should be in the range of atomic fields. That is the most important one. So if we consider the ordinary light, so if you use the ordinary light, you can achieve the non-linearity in the material because the strength is about less than 10⁻³ volt per centimeter. So it will not affect the atomic fields. Therefore, the optical parameters won't change. However, because the intraatomic field strength in the material is in the range from 10⁻⁷ to 10⁻⁻10 volt per centimeter. So if you use the ordinary light, it is of the order of 10⁻⁵. So that is not sufficient to change the material optical optical parameters of the material. Therefore, if we consider the laser light, it has a strength about 10⁻⁷ to 10⁻⁴ volt per centimeter. Therefore, we'll be having, that means we used to have the laser light to induce the non-linearity in the material that you cannot achieve using the visible, that is ordinary light. So this is about the non-linearity, what I said. So whenever the laser light beam passing through the non-linear, preferably that I will say non-centrosymmetric materials, gives rise to vibrations at harmonics of the fundamental frequency, that is omega, and then it reduces the wavelength by 2 times, or it is increasing the frequency by 2 times because energy equals to h nu or hc by lambda. So if frequency is increasing 2 times, means wavelength is going to decrease by half of that one. So it halves the wavelength or doubles the frequency of the incident light, and this is called as frequency doubling. So here we are supplying input frequency of the light as omega, and at the output we'll be getting 2 times as that of the incident. So this is called as frequency doubling, and this concept was observed by Franken et al. In the year 1961. So here he has used 6493 angstrom, that is ruby laser. So this is the one that I selected from the paper he has published by Franken in the physical review letters in the year 1961. So this is a block diagram that what he said. So he has selected the ruby laser, which is passing through the quartz crystal. So when the light is ruby laser light, that is 6943 angstrom. So when it is passing through the optical crystal, it gives 2 wavelengths. One is same light, that is 6943 angstrom, and other one is half of that one, that is 3,400 roughly angstrom. So when this one is passing through the prism, because of the dispersion, those light can be separated, so that can be recorded on the screen. So here the wavelength is reduced by half of that one, means frequencies doubled. So this is called as non-linear optics, called as second harmonic generation. So later on, the scientists demonstrated that we can also use the potassium dihydrogen phosphate, that is called as KDP crystal, where that crystal is converting the infrared light of wavelength 1064 nanometer into visible light, that is 532 nanometer. So it's converting the IR light that you observe, IR, and 532 is the green light. So IR light can be obtained using NdArc laser, neodymium, yttrium, aluminum garnet laser. So when this IR laser is passing through the NLO medium, it gives the output that is 2 times the frequency or half of the wavelength, that is 532 nanometer. The phenomenon of doubling the frequency is referred as second harmonic generation. The materials through which the SHG can be observed, so they are called as NLO materials or nonlinear optical materials. So which are the materials which are suitable for the SHG generation, that is second harmonic generation? So for this one, we require the non-centrosymmetric crystals. So we can't achieve the SHG, that is second harmonic generation, in the centrosymmetric crystals. So in case of centrosymmetric crystals, there is an inversion center, that is for every point of x, y, z in the unit cell. There is an equivalent -x, -y, -z position. Therefore, the polarizability is for x, y, z is positive, and polarization for that -x, -y, -z is the negative. Therefore, susceptibility becomes 0. That's why we can't, I mean, second order susceptibility becomes 0, that is eta 2. Therefore, we can't get the second harmonic generation in the centrosymmetric crystals. So these crystals, that is non-centrosymmetric crystals, are the crucial because they can exhibit piezoelectricity, where they can convert electric charge generated under the mechanical stress, and non-linear optical properties, that is second harmonic generation. So where you can, for example, you can use quartz, KDP, ADP, lithium, neodymium, so these are all the crystals we are going to use as the piezoelectric materials, as well as second harmonic generating materials. So they have their own applications, specific applications. In photonic devices, the NLO materials are of great importance because nowadays we are using that is, we want to optimize the data, so we want to increase the storing capacity, we want to improve the communication. So, and also the unique design of devices utilizing photons rather than electrons for the transmission of information, that is nothing but optical fiber communication. So nowadays we want to send the information in the form of light rather than electrons. So that has established to invent new materials with distinct NLO characteristics. So that about the materials, that is nonlinear optical materials. So we can classify the nonlinear optical materials into 3 categories. One is organic NLO materials, inorganic, and as well as semi-organic. So what is this organic NLO material? So examples, urea, amino acids, etc. So in case of organic molecules, they are chemically bonded, interacting through, as you studied in the chemistry, weak van der Waals interaction will be there in the bulk media. And these materials show larger nonlinear optical properties compared to other types because they have pi electrons, pi mobility. Not only that, the organic molecules are possessing donor-acceptor association where the electrons can transfer from donor to acceptor. So because of this, organic materials are suitable for the NLO applications. So these organic crystals have great nonlinearity because they have pi electrons, whereas donor acceptor molecules, and because of that, the nonlinearity is increased and easier to structural modifications because we can substitute some molecules so that you can change the donor accepting concept and pi electron mobility, and they possess low dielectric constant. And organic crystals, they have high transparency and also high LDT, that is called as light damaging or optical damaging threshold, and inherent synthetic flexibility, and so on. So these are all the advantages of the organic crystals. However, there are some drawbacks such as poor physico-chemical stability because they are the organic molecules easily interact with the surroundings. It is difficult to get big crystals, and mechanical strength is also very less. So like this, these are all the few drawbacks in the organic crystals. Therefore, we can go for the inorganic crystals with to improve these drawbacks. That is potassium pentaborate and potassium dihydrogen phosphide, ADP crystal, KHP. So these are all the inorganic crystals. So in this one, they are chemically bonded with covalent and ionic interactions of molecular materials in the inorganic materials. So these materials can be able to grow in larger size compared to organic and are easy to prepare. The gold crystals from this material will have higher mechanical and thermal stability because these are the inorganic crystals. Their melting point is too high compared to organic, and hence they have higher mechanical strength as well as thermal stability. So in comparison to organic materials, means organic crystals, so inorganic materials are well known for their second order NLO activity, chemical inertness because they won't easily interact with the surrounding, and excellent thermal and mechanical properties. But the drawback is that these inorganic materials, they are poor in the absorption over the visible region, and also laser damage threshold, it is very less compared to organic. So this limits the applications of the inorganic crystals in the photonic devices. So in comparison to organic materials, it is repeated. So in order to overcome these organic and inorganic, so the people are focused on semi-organics because the semi-organic crystals are mixing of organic and inorganic. So due to the drawback of organic materials in the growth of device-grade crystals and the drawback of inorganic crystals having lack of non-linear attainability, led the development of new type of materials called as semi-organic materials. So which overcomes the drawback of organic and inorganic materials. So these semi-organic materials are hybrid of or the mixing of organic and inorganic materials that shares the properties of inorganic as well as organic molecules. Hence, in the present scenario, so the research is paying attention on the semi-organic materials that have the property of high NLO efficiency, high laser damage threshold, and good quality of mechanical, dielectrics, and transparency. So because of all these reasons, many of the researchers are focusing on semi-organic crystals. In view of this significance of semi-organic crystals, the current research work deals with the growth and characterization of semi-organic crystal doped by. So here, you can dope the organic or dye to the inorganic or metal ions to the organic. It becomes semi-organic crystals with the intention to improve the optical, electrical, thermal, and then mechanical properties as well as thermal properties of the host crystals for desired applications. How to grow the crystals? So in this one, so first we need to prepare the saturated solution. So that after that one, we need to stir that one using the magnetic stirrer to achieve the homogeneous mixture. Then we need to filter it to remove the impurities as well as undissolved molecules if it is there. So that is going to remove. And then keep it in the crystallization dish and cover with a thin polythene sheet with few pores in order to control the evaporation of the solvents. Just for the reference, that you see here how we prepared the crystals in the laboratory. So for this, we don't require any sophisticated instrument to grow the crystals. So just you can prepare the supersaturated solution. So if you sometimes we need to mix both organic and inorganic materials. So then if that's the case, you make separate solutions and mix up and make the homogeneous solution again by using the magnetic stirrer and then filter to remove the impurities or undissolved materials if it is there and cover with the thin sheet with small pores to control the evaporation. And after a few days, let us say 3 weeks, you can get the crystals. So these are the crystals, what you can see on the crystallization dish. You can use those crystals. Sometimes we'll go for the seed growth method to increase the size of the crystal. What is this seed growth means? When you grow if you keep the crystals to grow themselves for because sometimes to get the crystals they may take few months, 1 month, 2 months, 3 months. So then it is very difficult to get the crystal, good size of crystals. So then you select any one of the good quality which is free from the defects and tag it and dip into the supersaturated solution. And that is acting as a nuclear center. It attracts the molecules from the supersaturated solution, and then the crystal will grow in a larger size. So this is the one that what you can go. Sometimes this is a practical difficulties you may get it during the crystal growth by slow evaporation method. Sometimes what happens when you mix up the two crystals, you may get mixed crystals in the sense that the solute which is going to dissolve, which is going to saturate very fast, and some solute may take more time to saturate. So the solute which is going to achieve the supersaturation very fast, so that will grow the crystal initially, but the solute which is not attain the supersaturation, so it takes more time to get the crystal. So the molecules won't mix up with each other, even though it is homogeneous, but they won't, the impurity, that means the dopants will not mix up into the host material. Then we'll get the two different types of materials separately. So to avoid that one, we'll go for this seed growth method. What are the tools we need to use to characterize the crystals? See, our intention is to grow the bulk size, the doped crystals for the photonic applications. That is our motto. So how you can do the analysis? So first we need to analyze, that structural analysis. We need to focus first. Because when you add the dopants, the crystal structure won't change much. That you need to clarify using single crystal, that is XRD, single crystal X-ray diffractometer analysis, as well as PXRD, powder XRD, which are used to analyze the structure, crystal structure, space group, and then FTIR, which is used to know the functional substitutions. This is the structural analysis. And then optical properties. So mainly we are focusing with the crystals what we have that should possess wide transmission window and high transmittance. That can be analyzed using absorption method. And then about the linear and nonlinear optical properties, that is absorption and emission properties, and nonlinear optical properties, that is second harmonic generation, third harmonic generation, and laser damage threshold. So these are the optical studies that you need to study. And then if the dopant is magnetic materials like nickel, cobalt, manganese, then you can study the magnetic properties. Then if we add the dopants to the host like metal ions, even sometimes organic, the thermal stability may increase. So because the thermal stability is also significant for the application. So that you need to study what is the limitations. And then the dielectric properties as well as mechanical properties. And then stability of the crystals under extreme conditions, that is under the influence of high energetic radiations like laser light and gamma radiations. So sometimes upon doping, some of the materials may enhance the biological properties of the host. So nowadays, the biological studies is also included along with these characterizations. So these are the instruments that you can view. So the first one is single crystal XRD, and then powder XRD, second one, which are used for the structural analysis. Second one is EDAX analysis to know the elements which are present in the crystal. FTR to know the functional groups in the crystal. And fourth, that is the next one, that is UV visible studies, that to find out the transmittance as well as energy gap of the material. First one is thermal studies to know the thermal stability of the material. So up to what temperature you can use that crystal for the application, that can be studied. And dielectric properties can be studied using LCR. And mechanical properties can be studied using Vickers hardness tester. And third harmonic studies can be studied using jet scan. Now, this is about, so far I covered what is crystal, and then what type of crystals you're supposed to select for the analysis. Is it organic or inorganic or semi-organic? What are the characterizations that you're supposed to study to know its potentiality for the applications? Now, I would like to explain with some examples by considering potassium dihydrogen phosphate and ammonium dihydrogen phosphate, that is KDP and ADP. So, of course, a lot of research work has been done on these two crystals, but still, research is going on in order to tailor the properties of the KDP and ADP by doping. So why the people have studied the KDP and ADP? Because the KDP is an excellent inorganic NLO material. It has wide transmission window, and also it has high laser damage threshold, and it is used to generate the higher order harmonic generators, not only first and second, that is second and third, even if you can go up to fourth harmonic also. And it has high NLO efficiency, dielectric permittivity, and piezoelectric effect, and piezoelectric properties. And easily you can grow the larger size crystals in the laboratory. Similarly, ADP is also exhibiting the same kind of properties as like KDP. So therefore, the lot of research work is going on these KDP, that is KDP and ADP crystals, by adding the dopants to enhance the optical, that is linear and non-linear, thermal as well as mechanical properties of these two to improve the potentiality. So these are the crystals which I grown, means some of my research students have grown in the laboratory. That is L-ornithine. It is one of the amino acid which is non-centrosymmetric, and it has both donor and acceptor, that is ammonia and then COOH group is there, NH3 and COOH. So because of that, it when you add this LO, that is L-ornithine, to the KDP and ADP, it has enhanced the linear non-linear optical properties as well as the dielectric properties. So these are the few crystals that you can see, that crystals. So we have added the dopant, that is L-ornithine is the dopant, L-ornithine monohydrochloride with different mole percent, to know what is the limitation of the dopant. Because you can't add the dopant as you wish, we should go from minimum to certain extent. So after that, the dopant going to diminish the properties of the host. So this is the other type of crystals. So here, in the previous one, I considered L-ornithine. So in this one, when this organic molecule is doped to the KDP and ADP, where the dopant is distributed uniformly over the entire crystal. Whereas in this one, the same type of crystals, KDP, ADP, as well as KHB also I considered. So here, I consider the dye, like fluorescent sodium, eosine, xylenol orange. So these are the fluorescent dyes where they can emit the fluorescent light with high intensity. So when you added those type of dyes, you can observe they are going to accommodate certain planes. They are not distributed uniformly. They occupied particular planes in the crystals. So if you see the first one, it is a xylenol orange doped one to the KHP. So the half of the crystal is transparent and half the crystal is colored. That is the presence of dye. Similarly, the second one is eosine doped one. And next one is also the same thing, xylenol orange doped one for KDP and ADP crystal. And last one is fluorescent doped one. So if you see this distribution, sometimes we may get uniform distributions. So sometimes the dopants may occupy particular planes. So why they occupy particular planes? For example, I have added xylenol orange to the ADP crystal. So as you know, the crystal, it is an anisotropic, which causes different phases will have different chemical and physical affinities of the dyes. And hence, the different surfaces are possessing different electrostatic potentials. Because of that, of course, xylenol orange is a larger dye, so it has a sufficient space to occupy particular planes. In the ADP crystal, it occupies 100 phase. Now you can observe the emission of light. One is considering the short and long wavelength of UV light. So when the xylenol orange doped KHB crystal is illuminated with short UV light, it is almost orange color. It is same as the dye. But when it is doped, when it is illuminated with the long wavelength, the color is slightly changed to greenish. So now the color, therefore the crystal is acting as a base for laser dyes to emit the different colors. So these are the results what I observed. So as I said, we are going to use different characterization tools for the analysis. So for structural analysis, we are going to use XRD, that is single crystal XRD, as well as powder crystal XRD. So already the single crystal XRD data is available because a lot of work has been done on ADP and KDP crystal. So we have added L-ornithine monohydrochloride to the ADP crystal. So when you observe this, whenever you are doing the means growing the crystal for the doped crystals, always you try to grow the host crystal as well as the doped crystals together, because we need to maintain uniformity. Okay, we should not select the data from the available one. We have to grow the crystals, same that is host crystals and doped crystals in the identical conditions, and we have to compare the data with the host. Now you see the black one is the pure ADP, that is the powder X30 crystals. So you can observe, means from this one you can study about the crystallinity of the crystal based on the peaks. So upon adding the dopant from 1 to 5, you can observe there is the variation in the intensity of the diffracted light, diffracted peaks, as well as the peaks are slightly shifted either towards right or left. You can expect. So that infers the incorporation of dopants into the host. And also because of if the intensity is increasing in the sense that the crystallinity is improved. So this is the increasing of crystallinity is significant factor to improve the optical properties. Now the second one is that optical. So as I said, we are focusing to enhance the transmission, means absorption should decrease. Absorption decreasing means transmission going to increase, because these two are inversely. Now you can observe the first two graphs. So upon increasing the doping concentration for KDP as well as ADP with the LO, that is L-ornithine monohydrochloride, the absorption is decreasing. So absorption decrease means transmission is increased. So my achievement means what I wanted is I want to increase the transmittance of the KDP and ADP crystals. So now I have achieved by incorporating LOA, that is L-ornithine monohydrochloride. So using certain equations, you can also determine the energy gap. So whenever that means as the energy gap is increased upon increasing doping concentration, means the transmission window, that means it is going to allow the more amount of light through the band. So that is important for the optical communication. Next one is about dielectric properties. So the important concept to study the dielectric properties is that, so whenever we have the dielectric materials, they should possess lower dielectric constant at higher frequencies. So now in my case, if we upon adding the dopants, the dielectric constant is decreased. So if the dielectric constant decreases means dielectric loss, that is as you studied in the physics. So dielectric loss means whenever you apply the electric field across the dielectric materials, the energy is dissipated in the form of heat. That is the name of dielectric loss. So now the dielectric loss is decreased upon adding the dopants. So that enhances the optical quality of the crystal. Now I studied the optical properties, dielectric properties. Now about the mechanical stability. So that you can study the mechanical stability by considering by studying the Vickers hardness tester, study an instrument. So here, upon doping the ornithine monohydrochloride to the KDP and ADP, in both the cases, the dopant enhances the mechanical strength. That is, the metal can withstand higher load without damaging. So because of that, you can use these crystals under extreme stresses also. That is called as device fabrication. So it should processing. So when you want to use the crystals for the optical devices, so we are focusing a little bit, not only optical properties, so mechanical strength is also important part. The enhancement in the hardness will have considerable influence on fabrication and process, such as easy in polishing and less wastage due to cracking and breakaging of the materials during the polishing. Next, efficiency. That is nothing but nonlinear optical efficiency. So we bring the KDP, that is potassium dihydrogen phosphate, as a reference crystal. So with respect to that, we determine the SHG efficiency for the doped material, and also we measure the laser damage threshold value also. So for pure KDP, LDT value is 0.2, that is gigawatt per centimeter square. But upon doping, it is increased, enhanced very much. It is about 3.39, and SHG efficiency is about 1.85 times of the KDP. Even for ADP also, SHG efficiency is enhanced and also increased. Therefore, the upgrade in the SHG efficiency implies that this material is responsible for the optical modulation and also in the frequency conversion devices applications. So the tolerating of the laser radiation is an important property of the NLO material. The optical destruction in NLO sample affect the competency of optoelectronic instruments. So that's why LDT is also significant. So this is another material that is the dye-doped one. That I want to show about the thermal studies, because in the earlier cases, thermal study did not change considerable upon doping. But in this case, when the dye like fluorescein is doped into the ADP crystal, the thermal stability is enhanced from 197 degrees Celsius to 202, hardly. So that is the only that you can't expect too much of increase in the thermal stability. So about 4 to 5 degrees Celsius, you can expect the enhancement. So that is enough. Even for the same material, in this case, the hardness is slightly decreased, of course. So even though SHG efficiency is enhanced, and then thermal stability is enhanced, energy gap is also improved, but mechanical stability is slightly decreased. So this is about this nature. Okay, so you can't expect that for don't expect that upon doping all the properties are going to improve. Some of the properties are going to improve, some of the properties are going to decrease. Now let us about applications of the crystals in the photonics. So first one I'd like to highlight about in laser technology. So as I said, second harmonic generation in the sense that whenever you pass the light of particular wavelength through the NLO crystals, the frequency is doubled or the wavelength is decreased half of its value. That is, if I pass the light of 1064, using that is IR, that is infrared region, then it is going to, the output of the light is through the material is about green light, that is 532 nanometer, because of second harmonic generation. So that expands the range of the laser wavelength and making it versatile for industrial and scientific applications. Okay. So as and when you change the wavelength or frequency of the light, so just you pass the light through the crystals so that you can change the wavelength or you can change the frequency for your applications. So that is the one that what they are using in the semiconductor lithography by reducing the wavelength of light to less than 200 nanometer. That is deep ultraviolet crystals we are using. Next one is about telecommunications. So in this one, again, in the as you know that we are sending the information in the optical fiber in the form of light, not in the form of electrical signal. So so for that purpose, we have to send the information in the form of light means with a specific wavelength is required for the communication purpose. So for that, optical communication system for wavelength conversion and signal processing, we are going to use the NLO crystals, and that enable high-speed data transmission by generating new frequencies through second harmonic generation or using parametric process. And next one is multi-photon microscopy. As you know that sometimes it is a little bit about medical application. In the tissues, there are some organic molecules which are so fluorescent. If you want to get the emission of light from the fluorescent molecule, you need to excite the molecule with specific or particular wavelength where you have the maximum absorption. Then only the molecules are going to emit the light. That is the name of fluorescent molecule. For example, you consider NADH. This is one of the dye which is present in the tissue that emits the blue light. FAD is emitting about green fluorescent, which are present in the mitochondria. Similarly, tryptophan is also one of the organic molecules which is present on the entire tissue. So this fluorescence emission going to hinders when it is affected. For example, something is some of the cells are affected due to the tumors. So whenever the tumor is formed, then automatically that is a unwanted cell that is going to hinder the fluorescence because it forms the clusters over the fluorescent molecule. And whenever the intensity of fluorescent is changed, that can be analyzed using the mapping process. So that enables, so that means using NLO crystals to generate the ultra-fast or high-intensity laser pulses that excite the fluorescence molecules which are present deeply within the tissues. So for that purpose, we are using BBO, so beta barium borate crystal, or LBM, that is lithium triborate crystals, are used for making the live cell imaging and long-term studies. And also we are using the crystals in the integrated photonic circuits, that is organic and semi-organic NLO crystals are being developed for electro-optic modulation. We're also using these crystals for optical switching as well as data storing. So electro-optic crystals in the sense that, so whenever you apply the electric field across the crystal, the refractive index of the material is going to change. So whenever the refractive index changes, then the energy of the light passing through the material is also changing. So lower the refractive index, lesser the dispersion. So the light can pass without any dispersion or scattering. So that's why the refractive index is the key factor here. That's called a bare reference. So coming to the conclusion. So designing of the NLO materials in the field of crystal growth is a great potential area. So it is evident from the discussion what we discussed so far, that is organic dope, dye dope, as well as metal ion dope crystals. In few cases, dopants have improved the properties of the host crystals, not always. And in some cases, doped crystals have failed to encounter the standard required for the practical use in the device. So that is the research that what we want to do. So hence, generating the crystals of considerable size, quality is extremely challenging. So if researchers achieve these criteria, nonlinear optical materials offer wide range of applications in optics and related sciences. So materials with high nonlinearity are receiving a lot of attention for the device applications. So thank you.
Thank you very much, sir, for that insightful and informative session on nonlinear optical crystals. Your presentation has helped us understand the fundamental concept as well as the practical applications of nonlinear optical crystals in modern photonics and research. I'm sure all the participants found this session highly useful and intellectually stimulating. Now, The session is open for discussion. Is there any questions from participants? You can put your questions in a chat box. I think there is no questions from participants. Now it's time to curtain today's technical session. On behalf of Sri Siddhaganga College of Arts, Science and Commerce for Women Tumkuru, I sincerely thank Dr. Suresh Kumar HM, Professor, Department of Physics, Siddhaganga Institute of Technology, Tumkuru, for taking time for his busy schedule to share his valuable knowledge and experience with us. Thank you once again, sir.
Thank you very much.
I also thank all the participants for their active participation. Kindly remember to fill out the feedback form, which will be shared in the WhatsApp group later. We will look forward your participation in the upcoming sessions of this faculty development program. Thank you. Thank you one day long.
Thank you, sir.
Correct ಆಗಿ sir.